Assalamu alaikum. Am I audible?
Yes, sir.
Yes, sir.
Let me fix my speaker in a bit and then we will start inshallah. All right, so we'll get started. So this session will be recorded. If you don't want yourself to be recorded, make sure you turn off your video and the mic as well. Okay. In case you have any questions, you can raise your hand. I will give you the opportunity to ask. You can either unmute yourself and ask the question, or you can also write it in the chat as well. Okay. All right. So let's get started. Bismillahirrahmanirrahim. So in our last class, we discussed about reinforcement learning, and we saw how we can use uncertain situations or uncertain outcomes to our advantage and make the best of it. Today, our discussion will center around probability, which is going to further the discussion of how we handle uncertainty. Okay. So probability is basically the model of uh, probability is basically how we model or compute under uncertainty. Uncertainty. That is the basic task. Okay. So if you can recall what we discussed in the first class when we discussed the history of AI, we said that during the first decades, people tried to write down lots of rules and try to chain them together, right? And that gave rise to interesting competition for things that actually follow those kinds of rules. Okay. But the problem was it did not scale because of uncertainty. All right. So the problem was we did not have methods to cope with the uncertainty. And today we are going to learn a tool that is going to help us discuss about probabilistic reasoning. Okay. So before doing that, we will have a preview of all the little things that are involved with uncertainty. Okay. So you have probably seen all of these in the previous courses. This will serve as a bit of a refresher. Okay. So we will start our discussion with a running example problem. And the problem is of Ghostbusters. Okay. So this game is going to illustrate what is involved in accumulating and managing evidences based on uncertainty and how frustrating it is to not have something to help us. Okay. So the help that we are seeking is to compute something called the posterior probability of variables that we care about given certain events. Okay, given we have some observations about the world, we want to compute some probabilities. All right, and the probabilities are associated with some queries that we want to answer. Okay, so the way this game works is we have this board. Okay, this blue board here, and somewhere in this blue board there will be a ghost. Okay, we do not know where the ghost is. Our job is to figure out where it is. Okay, so there are multiple possible actions available to us. The first action is called bust action. Okay. When what we say is that we point to a certain cell, let's say probably this one, and then we say that, okay, there is the ghost. Okay. So after this action is executed, if we are correct, that means if there's actually a ghost there, we win the game and get, let's say, lots of positive points. Okay. But if we are wrong, we lose the game and we get a lots of negative points. Let's say. Okay. Now, before making any guess, since we do not know where the ghost actually is, there is another action that we can do that is called sensing. Okay. So each sensing action will give us a color and it also costs us a small negative point. Okay. So whenever we do a sense action on a certain cell, it gives us a negative reward or negative point, okay, negative score of some sort, and it will also give us some color. Okay. So what is the meaning of the color? So whenever we sense a cell and we get the color red, it means that uh, we are sensing a cell that is right on top of the ghost. So as you can see here, let's say the ghost is actually hidden in this cell. And if we sense this cell, we will get the color red. Okay. So then we have the color orange that tells us we are 1 or 2 moves away from the ghost. That means 1 or 2 cells away from the ghost. Then we have yellow that is 3 or 4 away. Then green that is 5 or more away. Okay. Okay, the ghost is pretty far. So this is the sensing action, and there's some uncertainty associated with the sensing action in the sense of noise. Okay. So you can see a table where we have a bunch of probabilities of color given distances. Okay. So for example, this one indicates that if the ghost is 3 steps away, 3 cells away, the probability that you get a red is 0.05. Okay. So that means that even if you sense in, let's say, this cell, okay, there's a possibility, that means there's a 5% chance that the sensor will give us a red reading. Okay. All right. So similarly, we can get probabilities for all the colors and all the distances. Okay. Some of them are listed here, some of them are omitted, but I hope you get the idea. Okay. So the problem here is that it might happen that you are sensing right on top of the ghost, but due to the noise, you get a green color. Okay. Or it might happen that the ghost is very far away and you're getting a red. Okay. All right. So that is the scenario that we have. So with that in mind, let us try and watch one such game. Okay, how it can play out. Okay. So this is our game. Initially, we do not know anything about the cells. Okay, so all the cells are blue, and we have to find out where the ghost is. So initially, we will do some sensing actions, and then we will go for busting. Okay. So if we play the video, you'll see that the first cell that we get is green, so not very close. We get a red here, very likely, but then again, we cannot be sure. So we might want to try and measure around that position. So orange, lots of greens. Okay. So you can see green again, green again. So since we see lots of greens around the red, so there's a probability that this red might not be a ghost, it might be a noise. Okay. So we are seeing a bunch of oranges now. It looks more promising. Oranges again, green, it might be a noise, red, lots of oranges. Okay. So at this point, we might decide that, okay, this red position looks pretty good, the right red, right? So we can take a chance and see whether this is correct or not. Okay. So remember, we saw 2 reds here, one on the left and one on the right, but the left one is most likely a noisy method based on what we saw around it. Okay. So we might take the bust action for the right red because it has oranges surrounding it, which gives us a more chance. Okay. So we go for the bust action and you see there's a hit. That means the ghost is there. Okay. So consider what we did here. Okay. So first, we did not know the exact position of the ghost. All right. So our choice was to sense a bunch of cells. Okay. So what you can see here is we sense this cell here, and we saw that there's a red. Okay. It indicated that there might be a ghost possibly there. But we were not sure, as we knew that there's a 5% chance that this red is a fluke, right? So to be sure, we sense around it. Okay. And you see that even though there's an orange here or there's a yellow there were a bunch of greens. Okay. And we also know that one green might be wrong. Okay. That is why we made multiple groups that helped us decide that, okay, this cell might not be it. Okay. On the other hand, if we consider this red cell, okay, here, coloring red with red, not the best idea. So we saw a bunch of oranges surrounding it. There was a green here, which might be a noise, and we saw a bunch of oranges indicating the strengthening our notion that okay, there might be a ghost here. All right. So we decided to go for it. All right. That was the basic idea. Okay. So if we move on back to the slides. So the key takeaway here is to notice that how our decision changed throughout the game. Okay. So basically, we had some quantities that we didn't know. Okay. That is basically the position of the ghost. So in our model, we represent this using something called a random variable. Okay. And our uncertain outcome that we don't know. Then there were some other quantities that are the results from the sensor probes, which we knew. Okay. We also knew how the things that we know are probabilistically connected with the things that we do not know, okay, or the things that we care about, basically. All right. Then we got some results, some green cells, some red cells, some orange cells, and in our heads, we did some calculation to make a decision that, okay, we will go for this red cell. Okay. That is the basic idea. Okay. Any questions so far? No questions. All right. If you have questions, feel free to raise your hand. I will stop and ask you. Okay. So let us try to generalize the situation. So in any scenario, we will have a collection of variables. These are going to be random variables because sometimes we know their values and sometimes we do not know their values. When we know the value of a random variable, that is called evidence or observed variable. Okay, we are going to know certain things about the world, like the sensor readings that we saw here. Or let's say if you're doing, let's say, for example, medical diagnosis, let's say, in that case, the random variables can be the symptoms that we observe from the patient or the lab test results, okay, that we get. All right. Then there will also be some unobserved variables. These are the things that we do not know the value. So, for example, in the Ghostbusters case, we do not know the location of the ghost. Okay, or we also do not know what will be the color of the cells that we have not checked yet. Okay, and continuing the medical diagnosis example, this could be the test results or the tests that the doctor did not perform. Okay, but still good. All right, something like that. Okay. Then we have this query variable that we actually care about, that we want to know about. That is where the ghost is actually. And finally, there might be some other variables that are helpful. Okay. So we will model all of these things and we will need to figure out how to work with all of these things to do probabilistic reasoning. Okay. So the way we define the model, which has been used in many cases throughout this course, you might have seen models throughout. So the model is the description of how the known variables are related to the unknown variables. Okay. So in today's class and the next class, this is going to look like a giant table containing something called a joint distribution. Okay, so that will be a big lookup table containing lots of probabilities. And the way we are going to deal with that is using something called probabilistic reasoning. Okay, it means that we will take the evidence that you have, we will do some computation to produce quantities that we can use to make decisions about things that we want to know. Okay, so in our running example that we have for Ghostbusters, that basically translates to where should we probe next or where the ghost might be. Okay, these are the sort of decisions that we want to do. All right. So this is the generalized scenario. If you don't have any questions, let us move on. And so we will start with the basic definitions, the basic ideas of probabilities. First, we have random variables that are aspects of the world that we care enough to put them inside our model. Okay, we give them some name. So let's say, for example, R might represent whether it's raining or not. T might represent whether it's hot or cold. T might represent how much time does it take to drive to our work, and so on and so on. Okay, so these are things that we can observe or we might want to query about or infer about. Okay, there might be some other variables that help us write down how the world works in a probabilistic way. Okay, so these are similar to CSPs in the sense that these variables have domains. So for example, is it raining or R variable might have a domain true or false. Okay, so uh, so one special notation that we use is like this. So let's say whenever we have a Boolean variable like this, that this one can be true or false, R can be true or false, we often write them like this. Okay, so instead of writing, let's say R equals to true, we will take the small letter plus R. Okay, that will indicate that this is a true event. And similarly, minus R indicates a false event. Okay, we only do this when the names aren't ambiguous, of course. If the names are ambiguous, we will use the full assignment operation. Okay, fine. So there might be other types of variables like T, which can be, let's say, hot or cold. Okay, this is a binary variable similar to the previous one, but it's not clear. Okay, then variables might be continuous, like the time taken to go to your work might range from 0 up to infinity. Okay, or your variables might have some structures, like let's say ghost position can be a location pair. Okay, let's say 0, 0, 0, 1, and so on and so on. Okay, so in general cases, whenever we discuss probability in this class, we discuss the discrete cases. Okay, but the things that we discuss can apply for the continuous cases as well. But the continuous cases are a bit more complicated in the sense that, let's say, for example, if you have summations that will turn into integrals, and you will also care about corner cases and whatnot. Okay, so for now, we will stick to discrete cases. So remember, random variables are similar to CSPs in the sense that they have values from a particular domain. Okay, but what is new here is that each variable has probabilities that are associated with the individual values that we can assign. Okay, so for example, the temperature might be hot or cold with certain probability. Okay, so we will have something called a probability distribution associated with our random variable that will assign a number to each possible outcome. Okay, so for example, here we have a 50-50 chance of having either hot temperature or cold temperature, right? So these numbers will definitely have certain properties, like they will be positive, they will sum up to 1, and so on and so forth. Okay, so here's another example. We have weather. It's still discrete, but it's not binary anymore. So this says that the sun, the weather being sunny, has a probability of 0.6. That means 60% chance, rainy 10% chance, 30% chance, and meteor has a 0% chance. Okay, so this is actually a well-formed probability distribution. But whenever we are designing an agent, we might want to avoid this 0. Okay, we would probably replace that with 0. Let's say 0.00001, very small value. Okay, because once we put 0 in our probabilities, weird things happen, and which we will see later, hopefully, if we get time. Okay, so whenever we put 0.00001, what we really want to say is the meteor is really much unlikely, but should evidence come into our observations that is consistent with that outcome, but let's say not the other outcomes, we want to conclude it anyway. Okay, that is the basic idea. So we only put zeros in things that will never ever under any circumstances happen. Okay, otherwise we will put some value or a very small value. Okay, so the unobserved random variables have distributions that are shown in the table. So when we talk about distributions, we refer to these tables. So when we write, let's say, P of W, like this, the capital W, it's basically a dictionary or a hash map. Okay. So that means that we have a probability for every value of the domain of the variable. Okay. That is our probability distribution. But let's say whenever we write P of W equals to rain, this is not a dictionary anymore. That is a single scalar value. Okay. So that is basically the probability that the weather will be rainy. That gives us a single number. Okay. So to summarize, P of W is the whole table. But whenever we write P of W equals to rain, that is basically a single entry in the table. That is this entry, right? Fine. So again, in order to be a legal probability distribution, all the entries must be non-negative, of course, and they have to sum up to 1. And 0 is allowed, but it's usually a bad idea in practice, and we will talk about it later on, inshallah. Okay. So there's also a shorthand notation that we often use. Usually, whenever writing a probability for a certain event, let's say, I did not talk about event yet, okay, no problem. Certain outcome, let's say hot, we drop the variable equals portion. Okay. So this t equals to hot, here t equals is dropped and it's written as p of hot. Okay, when things are unambiguous, of course. Okay. So if the t is the only thing that can be hot, we will directly write p of hot. Okay. But let's say if there are multiple variables that can be hot or cold, we have to write the variable names as well. That is the basic idea. Okay. Everyone good so far? Any questions? No questions. All right, good. Moving on. So we move on to joint distributions that are the heart of the probabilistic models. Okay, so they will possess all the information about the domain, about all the variables and all the interactions among them. Okay, so joint distributions are usually very big, so we tend to avoid computing the whole thing if we can. So they are basically similar to your state spaces. They are too big to write down, but if you use them in the right way, you can do anything that you need in a probabilistic model. Okay. So a joint distribution over a set of random variables specifies a probability for every possible assignment. Okay. An assignment here is just like CSVs. It's an outcome containing each value assigned to each variable. Okay. So this can be written in this way. Okay. So we have P of x1 equals to x1, x2 equals to x2. Here, the capital ones are the variables and the small letter ones are the values. Okay. So usually we shorten it like this. Okay. Instead of, again, we omit the variable equals portion and we only write the values. Okay. Fine. So if we have all the capital letters there, whenever we put all the capital letters here, usually let's say P of x1, x2, x3 capital letters, they are basically an n-dimensional array, even there are n capital letters. Okay. So n is the number of all the possible, n is the number of variables. But when we assign values to each random variable like this one, we get a single number, a single value. Okay. So on the right here, you can see a table that is a joint probability for temperature and weather. Okay. For simplicity, we are considering both of them to be binary. So we have hot and sun, hot and rain, cold and sun, cold and rain. Okay. And we have a bunch of probabilities associated with it. Okay. So from this, we can answer any question that you might have about the temperature and weather of this model. Okay. And we will see that in a minute. All right. Again, the distribution obeys some rules. The rules are we have non-negative probabilities and they should sum up to 1. Okay. Now, one of the problems with joint distribution is that it's the size. Okay. So the joint distribution table can be used depending on the number of variables and the number of values we can have. Okay. So let's say if we have n variables and each variable has a size d, that means that domain size is d, can anyone tell me how big the table will be? Raise your hand if you can tell me. We have n variables, each of them can take at most d values. Okay, ID242, you want to try?
Yes, sir.
Yes. What
Or
should be the
if you have n values and each of them can have d,
yes,
then it will be d to the power n.
d to the power n, exactly. Right, thank you. Your ID is 242, right?
Yes, sir.
Okay, so to explain, so what does this table have? Consider what do you want to store here? So we will have each of those variables, x1, x2, up to xn, right? So it will contain up to xn. Then for each of them, we will have every possible assignment. Okay. And for every possible assignment, for every possible combination of the assignment, we can get a probability value, right? So we will have one number for each variable assignment, and there are exponentially possible combinations of that. So we get d to the power n. Okay. That is the size, that is how big the table is. Okay. So the problem is any real graphical model can easily have thousands of variables. So we can never write the whole joint distribution table. Okay. So this is in the same way that we can never draw the entire state space. Okay. But remember, that did not matter during the search, right? Because we only needed a part of the state space that we found during our search process. Okay. We started from the top and we were selective about creating and expanding the search, which gave us a quick solution. Okay. Well, in probability, it's going to work a little bit differently here, but still, we will try to be careful about not drawing the whole joint distribution table. We will only build the portions that we need on the fly. Okay. All right. But for simplicity, today, we are going to stick to the entire thing just to understand all the concepts that we have. Okay. So with joint distributions out of our way, we can move on to a probabilistic model. So a joint distribution over a set of a random variables is called a probabilistic model. Okay, so to reiterate the whole idea, we are going to have a bunch of random variables with their domains, and the assignments here are called the outcomes. Okay, so the joint distribution will specify how likely each outcome is. For example, hot and sun together is quite common. That is why we have a 40% chance, right? Okay, but hot and rain together is pretty rare. Right? That is why we have 10% chance. Again, these distributions are normalized, and you're going to hear this word a lot. Normalized in this context means that when you add everything up, you get 100. Okay. And ideally, we will have a certain number of variables that are going to interact. Okay. Not everything will interact with everything. So we will pick and choose a bunch of variables that we care about, and then we will build our probabilistic model based on their interactions. Okay, so this is going to be the key in building efficient inferences over huge models. Okay, not every variable is connected to all the variables. Okay, moving. So we move on to something called events. Events is a set of outcomes. So remember, an outcome is a complete assignment of all the variables. So whenever we talk about the probability of a certain event, there are multiple assignments that will match the event. If there are multiple assignments that match the event, then we have to sum them up. Okay. So what does that mean? So as said earlier, from the joint distribution table, we can calculate the probability of any event. Okay. So let's say we have a class of events that we want to care about, that we want to get the value of. So what do we do? So let's say, for example, if we consider this question, what is the probability that it's hot and sunny? Okay. So that is basically, to answer this question, we go to the joint distribution table. That is basically this row. Okay. Hot and sunny. Okay. So that gives us a single outcome, and the probability value gives us the value of the outcome. Okay, that is 40%. So the probability that it's hot and sunny is 0.4. Okay. So from the single outcome, we can get the value. How about the next one? What is the probability that is hot? Okay, it's not directly given in the table, correct? So we need to derive this from the table. So what we do is we see that, okay, we have two rows, this one and this one. That corresponds to the outcome where we have the temperature as hot, which is being asked in the query. Okay, so how do we get the total probability of being hot? We consider the values for these two rows and then we add them up to get 0.5. Okay, that gives us the probability that it will be hot. Okay, so notice that in this particular event, the value of this column did not matter. Okay, we had a single column for T for which the value mattered, and for others it did not. Okay, we will talk about this in details in a bit. So keep that in mind. So next question, what is the probability that it's hot or sunny? Okay, so we will have to find the rows that are consistent with hot or sunny. Can anyone tell me which rows will they be? Raise your hand. Yes, Rafael?
So the first three rows.
First three rows. So hot, we are looking for hot. Hot is here, sunny is here and here. All right. So we have three rows that correspond to the outcome that we are looking for. So we need to sum these three up and we will get 0.7. Okay. So as you can see that as the events get bigger, the probability is going to grow. Okay. Now, almost all the time in this class, that event that we will care about will be something like this partial assignment. Okay. Not probably the all events, but let's say probability of, let's say, hot, probability of sunny or something like that, right? Moving on, we will do a quiz, right? So if you can answer the question, you will raise your hand and I will ask you. Okay, so even given we have this joint probability distribution table, we will try to figure out the values that are asked. The first question, what is the probability that both X and Y are true? Remember, the plus sign indicates true. Okay, raise your hand if you can answer. Idris already answered. Someone else? What is the probability that X and Y, both of them are true? Yes, 212, Sakif.
So 0.2.
0.2. How did you figure out the value?
So from the table,
So from the table, which row?
first rows.
The first row, right? So the first row directly corresponds to the event that we're looking for. That gives us the probability 0.2. Thank you. ID 212. Okay. How about the next one? The probability of X being true. The next question. Raise your hand. Someone who already did not answer. Anyone? Yes, 216. What is the probability that X is 2?
Sir, 0.5.
0.5. Okay, how did you get that value? From which rows of
Sir,
the joint distribution?
From the table, we get first two rows.
First two rows. So both of
We
them,
sum their probabilities.
we sum their probabilities to get 0.5. Thank you. Your student ID is 216. Good. Thank you. The third one. The probability that Y is false or X is true. Raise your hand. ID 218.
So 0.6.
0.6. How did you get that value?
So for minus y to be true, we have 0.3 and 0.1.
0.3, that is this row and this row. And
for plus x to be true, we have 0.2 and 0.3. So 0.3 is common here. So
yes,
we're just adding 0.3.
so we basically have three rows that correspond to this outcome, right? So we sum them up to get 0.6, right? Your ID is 218. Thank you.
0.6.
All right. Fine. So that gives us 0.6 by adding up the corresponding rows. So let us move on to the marginal distributions. So their name marginal distributions come from the idea that you have this 2D table containing this joint distribution. Here you sum up the rows, write the results in the margins. Okay, that is the idea. So the thing here is, if we take a joint distribution, it says for every combination of multiple variables, what is the probability of that outcome? Okay, and marginal distribution is basically a smaller table in which some of the variables have been eliminated. Okay, so when you eliminate a variable, rows usually collapse together. Okay, so for example, if we eliminate the W here, okay, there is hot sun, and let's say for these two, the hot sun and hot rain will collide. Okay, they will collapse, they will come together. That they will come together means that they will sum up, because both of them have P of T equals to hot. And when values collide, you add the probability values together to get 0.5. Okay, so this process is called marginalization or summing up. Okay, so from the joint distribution table, if we want to compute the P of T, okay, so we will sum up all the values of S considering the given value of T. Okay, so if we want the probability T is equals to hot, we add up the probability of hot comma sun and hot comma rain to get 0.5. And the same goes for probability of T equals to 4, okay, which gives us 0.5 as well. Okay, we already did it intuitively. This is just a formal representation. Okay, in the similar fashion, we can also calculate P of W as well. Okay, and here we have here we have the probability of sun and probability of rain. Okay, with the temperature marginalized up. Okay, so the general formula looks kind of like this. It should be pretty easy to understand. Okay, any questions regarding marginal distributions? No? Then again, we will go for a quiz, simple quiz. So we have our joint distribution table that looks like this, and we want to compute the marginal distribution of P over X. So can anyone help me? Raise your hand. P of X. We want to calculate this one from the joint distribution table. Raise your hand. Yes, 204.
Half and half, because
Half and half. Okay, let us try to calculate. Okay,
so plus,
So-
sorry.
first of all, consider what we have for P of X. So for P of X, we will have entry for each possible value of X. All right, we will get rid of Y. Right. So P of plus X, that is which two rows? The first two rows, right?
Yes, sir.
Okay, that gives us 0.5. So for P of minus X, we have the last two rows, that gives us the same thing. Okay. There is another way to do it, is let's say once we have the 0.5 for plus X, we can say that there is only one other possible value. So we will subtract 0.5 from 1 to get the probability of minus X, because they have to sum up to 1, right?
Yes.
Okay. Thank you. Your student ID is 0.204. Okay, moving on. Let us calculate P of Y. Anyone else? Raise your hand. So what does P of Y entail first? P of Y entails calculating the probability for plus Y and minus Y. These are the possible values for Y. So we will go for ID 230 is hand first. 230.
Sir, for plus y, 0.6, and for
For
minus
plus Y, we have 0.6. How? Which rows?
Sir, first and third.
First and third row. That corresponds to the plus Y event. That gives us 0.6. And the second one is 1 minus 0.6 is 0.4. All right?
Yes.
Okay. Thank you. Your student ID is 230. Good. So I hope everyone understood marginal distributions. Okay. So here we have two variables, and we created marginal distributions using one of them. So in the joint distribution table, we might have, let's say, 100 variables, and we can create marginal distribution using one of them. So we would require a whole bunch of sums to get to the result. We could also create marginal distributions over, let's say, 99 variables maybe. The table would still be big. So any subtable, even the entire thing, can be called a marginal distribution. Okay. So any subtable or the original table of the joint distribution is the marginal distribution. Moving on. So conditional probabilities are the core concepts of conditional reasoning. Okay, here we deal with probability of A given B has already happened. Okay, so we have this Venn diagram here. So what do we have? We know that, let's say for example, P has already happened. So we know that this has happened for sure. Okay, so we are in this territory. We would like to know how likely it is that A will also happen. Okay, so graphically, we want this purple portion on the map. Okay, this portion is required. Okay, so mathematically, we do that by computing the ratio of the joint probability of A and B happening together. That is this one divided by the probability of B. Okay, so you can think of it as like that what proportion of the B outcomes are also A outcomes. Okay, so using this formula, we calculate the conditional probability given joint or and or merging probabilities. Okay, so let's do some examples here. So we have our previous joint distribution table here. We want to compute the probability, or what is the probability of weather being sunny given that the temperature is cool. Okay. So what do we need to consider? We need to consider two things. So it will be a ratio. On the top, we will consider what is the probability that it's sunny and cold. Okay. So the probability that it's sunny and cold at the same time is this one, right? That gives us 0.2. Okay. And in the denominator, we have the probability of the conditioning over C, which is cold. Okay. So what is the probability that the temperature is cold? The temperature is cold in the third row and the fourth row. That gives us 0.2 plus 0.3, which is 0.5. And finally, we get this result 2 by 5. Okay, so this is the probability that the weather will be sunny given the temperature is cold. Okay, so what did we do? We took the ratio that the probability that it's sunny and cold divided by the total probability of conditioning over C, which is cold, that gave us 2 by 5. Okay, so one thing that you can notice here, the numerator that we have here is also common in the denominator. Okay, when calculating the conditional probability. This will be helpful in the next class, inshallah. Okay, keep that in the back of your mind. All right, so we have something like this, 0.4. Okay, so any questions regarding conditional probabilities, how we calculate them? Right, then I have questions. So again, we will do a quiz on conditional probabilities. All right, so the first one. Raise your hand. What is the probability of X being true given that Y is true? Okay. All three of you answered already. Someone else? 201. Yes.
Sir, at first we need to consider the OI plus OI part. So in the denominator, we will
Denominator, we will have
0.6.
P of
0.6.
P of which probability? Tell me the probability.
Plus OI.
Plus Y, right? Okay. And in the numerator, we have
Plus X and plus Y.
plus X and plus Y happening simultaneously, right? So plus X and plus Y happening simultaneously is 0.2, and in the denominator we have plus Y. So plus Y corresponds to this row and this row.
Yes,
If we sum them up, we get
0.6.
0.6. That gives us 1 by 3, right?
Yes. Yes.
Thank you. ID 201. Right. Next, this one, raise your hand. Someone else. 237 raised his hand first. Hamid. So what is the probability that X is false given Y is true? So what will be in the numerator? Hamid, I think I can't hear you. Mic may not be working, or it might be following my side. Can anyone else hear Tamil?
No, sir.
Okay, it's fine. Hamid, you'll get your chance next time, inshallah. We will move on to Shadid, 219.
Sir, in the denominator, we'll have P of
Probability
plus
of plus y.
P of plus y and
Yes, and the numerator we have
of minus x comma plus y.
minus x comma plus y. That means both of them happening simultaneously. Good. So what will be the value of the numerator? It will be
0.4.
third,
Third loop.
0.4. Good. And in the denominator, we will have
Point.
this one and this one, right? These two rows correspond to plus y. We sum them up, get 0.6, right? That gives us 2 by 3. Okay,
Yes,
thank
sir.
you. Shadid, your ID is 219. Okay, fine. That is okay. How about the next one? Probability of y being false given x is true. 234.
Yes, sir. So in the denominator, there will be P of x plus y and the
In the
numerator
numerator, what will we have?
minus y
Minus
Um,
y and plus x.
plus x
Yes. And in the denominator,
plus x.
probability of plus x. So minus y plus x is row 3. Sorry,
Yes, sir.
minus y plus x is row 2.
Yes, this one 0.3.
0.3. Right? Thank you. And in the denominator, we have
0.5.
two rows, this one and this one, 0.5. That gives us 3 by 5.
Yes, sir.
Thank you. Your ID is 234.
Yes, sir.
All right. So I hope everyone understood conditional probabilities. With that, we are done with today's class. We will continue tomorrow, inshallah. So thank you everyone for participating. If you have any further questions, you can ask now. If you don't have, then you can wait.